Okay, so I'm going to start from the perspective of where my talk began. So it emerged essentially from the combination of, I was working with students on the dark matter problem and also reflecting on, can you still see me okay if I, all right. So my talk emerged from the combination of working with students on the so-called dark matter problem or puzzle in astrophysics, and then also thinking about how to best make the case that big history as a field offers value that isn't available just while working just within the confines of a standard academic discipline. Right, so I noticed some interesting parallels that I think will be useful to highlight as we consider where to focus our efforts as a community going forward. So I'm going to start with just an overview of the dark matter puzzle because it's just an interesting scientific problem in itself. And it's also, of course, very relevant to the resolution to the dark matter problem is going to have a lot to say about the cosmic history that we tell that's, a core part of big history. But then for my purposes, this kind of the second half of my talk, it's also a tangible illustration of a method of inquiry that I think big history can model more generally. So I want to kind of emphasize that. Okay, so I think I'm just going to do it this way. Hopefully. There we go. All right. So the basic question involved here is really just, it's pretty simple to state. It's just how much mass is within a certain region of space, right? So you can think about it just within this room, right? How much mass, how would you think about how much mass is there in this room? You can extend it out to the solar system, to the galaxy, to the universe as a whole, for that matter, or to clusters of galaxies, and then to the universe as a whole. And if you just think about how you go about trying to calculate how much mass there is, right? A starting point, for example, in this room, we could just count up the stuff, right? All of us and our masses, all the chairs, and so on. But of course, there might be things in here, we can only hope there might be primordial black holes floating through, or various, subatomic particles or whatever that are going through here that we might not notice, but they might add to the maps, right? So you can start thinking about being more and more clever about different ways that you can determine indirectly how much mass there might be that you can't see directly. So it's the same challenge in on the cosmology scale and the astrophysics scale, which is you can use just direct, the simplest way, if you're looking around the universe and you want to know how much mass is in the universe, you just start counting stars, right? That's sort of what astrophysicists do. You look at how many stars there are, you estimate the average mass of a star, and you go from there to figure out how much mass there is. You can also use gravitational effects to look for mass that you cannot see. So for example, if you see something orbiting something else, but you can't see anything it's orbiting, that can tell you that there's something there. It turns out that there are also, you can be more and more clever about the different ways that you can infer the existence of mass, and we'll talk about some of those. There are, for example, you can look at how mass influences the formation of structure, right? So how much mass was there in the past? The whole story that we tell in big history about, the 13.8 billion year history going from smooth and simple at one point to clumpy and complex later on, and how that evolves. So we're going to talk about some of those. But the puzzle essentially is that different methods for answering that question, how much mass is within some region of space in the universe that you want to focus on, different methods for answering that question give different answers, and the discrepancies show up in different amounts at different scales. Okay, so that's the dark matter problem, or the dark matter puzzle. And it's easiest to demonstrate for circular motion at the galaxy level, so I'm going to start there. If you just think about, this is a sketch of a typical spiral galaxy, could be our Milky Way, hence the sun. Some of you may be able to see the sun has a smiley face so that we know it's the sun. You can think about describing, the orbits aren't perfect circles, but for a first approximation, you can think about describing the orbits as circles so that it's simple to analyze. And there's really only two parameters that you need in order to be able to describe the motion, and that's the radius of the circle, how far it is from the center, and what the velocity is that it's going in orbit around the circle, right? And so the essential idea brought my trusty physics demo here so that we can really think about this concretely, right? The basic idea is if you see something in the universe that's going around in a circle, if you're a good physicist, you ask, why is it not going in a straight line at constant speed, right? What's keeping it in a circle? And in this case, the answer hopefully is pretty obvious, that there's a string, and I can feel the difference between if I swing it fast, I have to pull harder. I can feel the string pulling harder. Don't worry, it's a pretty stable string. I don't think it'll break. It hasn't so far anyway. If I change the radius of the circle, if I make it bigger at the same speed, it's actually not pulling as hard. If I make the radius smaller, right, it's pulling harder. So you can see that there's a relationship. And, this really simple case, down to earth case, turns out to be the essence of all you need to know to understand it on the more cosmic scale. And you can make it a little bit more quantitative. For circular motion, it turns out that the acceleration is given, a little geometry shows you that the acceleration is given by v squared over r. And that probably makes intuitive sense. If you think about the faster it's moving, the more it's having to change its velocity, right? And the smaller the radius, the more the velocity is having to change directions, right? And then if you apply, again, pretty straightforward physics, Newton's second law of motion then tells us that there must be a force toward the center in order to make it go in a circle. And so that just means multiplying by m, the mass of the object, the tennis ball or whatever it is. And so then you get that the centripetal force, the force toward the center, is m times v squared over r. Okay, so that's coming from the motion, right? In order to make it move in a circle like that, that's the force that must be there. And so then if you add to that the astrophysics piece, which is that we're going to assume that the forces are caused, generally speaking, by gravitational pull, right? So again, some approximations just to make it easier to describe, but you can do it more generally. Then you can say the rule for the force of gravity. I guess I'll point with my cursor. You can say the rule for the force of gravity, and then substitute that into the equation on the last slide, and then simplify a little bit, and you end up with this nice relation that the velocity of how fast something, a star, or it could be a cluster of gas, clump of gas or something, moving around in a circle, the faster that it's moving, or sorry, how fast it's moving is related to how much mass there is and how far away it is from the center, right? It's probably just a side note, but it's interesting to note that the mass of the actual object cancels out here, which is very useful because it allows you then to not need to know the mass of the thing that you're seeing in orbit. And it's, for those of you who like to think about these things, it's related to why everything falls on Earth at the same acceleration, regardless of its mass, right? The mass shows up both in the gravitational force and in the inertia. So just to notice that. Okay, so basically what this boils down to is that if we believe the basic physics and the assumptions made, then the velocity profile, right? If you imagine looking at different distances, back to my figure here, if you imagine looking at different distances away from the center of the galaxy at different objects orbiting around the center, you could do a plot of how fast they're moving, and you would expect that if all the assumptions are valid in this case, you would expect that the velocity profile should map the mass profile with a 1 over r in here, right? So for example, think about what you would expect for the solar system, right? So all the mass of the solar system is concentrated in the center at the sun. And so the mass is constant essentially for all values of r. And so you would expect the velocity profile to drop off as you get farther and farther away from the sun. The orbit should be slower, right? And indeed, that is what you see on the right-hand side here is a plot of this for the solar system, the different planets, right? They go slower the farther away they are. So it's falling off as 1 over the square root of r. The big surprise, the original work on this was Vera Rubin and colleagues in the 1970s, is that it's very, very different for the galaxy, right? So this is a sort of a caricature of an observer looking at stars or clouds of gas moving at different speeds around the center of the galaxy. And this is a plot of, as a function of distance, how fast are they moving? And they don't fall off with radius at all, right? They're so-called flat rotation curves. So that's the essence of the so-called dark matter puzzle, right? The implication, just to summarize, the implication is that there must be a great deal of mass we cannot see via light, hence the term dark matter, that nevertheless exerts a strong gravitational pull on the objects we can't see. Excuse me. Okay, and it's worth pointing out, it's important to point out that another possibility is that some of my assumptions are wrong there, right? Maybe the laws of gravity aren't what we thought. There are people who propose that and speculate about the possibility of alternative theories of gravity or even alternative theories of motion. At small accelerations, maybe something is different about how these behave. Okay, and then the other thing I want to emphasize is there's a wide variety of evidence on many different scales for this. So I just picked on this one because it's easier to understand kind of concretely. I'm going to very quickly go through just kind of a list of the different examples, just because it helps you see the way perspectives impact this question. So one is on the scale of galaxy clusters, actually even earlier than the galaxy rotation curves I was showing you. Zwicky in the 1930s studied the Coma cluster and found that galaxies were moving faster in the cluster than could be explained by the mass that you could visibly see. And this is sort of a modern day version of that. This is a famous plot, graph of the, what do I want to say? Picture, there we go. Famous picture of the bullet cluster, and where it's a composite of X-ray observations. So the pink is actually where the gas in between the galaxies is visible in X-ray. And the blue shading here is kind of a false color plot made of the where the bending of light reveals the gravitational pull. So it's called weak lensing. It reveals the gravitational pull of the presumably unseen matter around. So this is, another way of getting at, there's something there that we can't see. There's also evidence from a very different direction, which is that if we think about the elements that, the different isotopes, the composition of the universe in terms of how much of each element on the periodic table, it turns out that you can predict based on the physics of the early universe how much there should be of each element. But it's very sensitive to the conditions and to what kinds of matter were around in the early universe. And so, totally different direction, but that puts a constraint on what kinds of mass there can be. And the punchline for this is that it says that it should be about the amount of what we see in terms of visible normal matter, even though there are some other reasons that make us think that there needs to be a lot more matter. So we're starting to get this idea then that there's more mass than we can see, but it can't be normal matter, like what everyday things are made up of, right? So the puzzle deepens in that sense. And then another way to get at this, which again, from a totally different direction, looking at the cosmic microwave background from about 380,000 years after the beginning, reveals that basically the structure back then is related to how the mass was distributed then, and that impacts what structures can form later. So again, a totally different way, much more complicated in terms of understanding how it fits together, totally different way of getting at the amount of mass there needs to be. And again, it fits the picture of normal matter being about what we can see, but then some other form of matter that's at least 10 times more, right? So piecing together this picture. All right, so this is just kind of a summary from a review paper on this. The dark matter puzzle is this situation, that there's evidence from all kinds of directions that most of the matter is invisible. Most of it is also non-baryonic, meaning it's not made of, protons and neutrons and our kind of everyday things. And so this even brings in the particle physicists, that they're interested in from a totally different direction that doesn't have anything to do with dark matter in terms of the astronomy of why we need unseen matter. There's motivations for types of particles that are predicted by various attempts to modify the standard model of particle physics, right? So everybody's coming together. This is the picture I'm trying to give you, right? Is everybody's coming together from these vastly different directions, zeroing in on the same problem. And so I just sort of, to frame that, I just highlighted like different areas of research, different narratives, if you want to call them that are brought together by the dark matter problem. Basic cosmology, that's the basis for the whole big history framework that we use, right? Observational astronomy, people who look at galaxies and the motions of stars around galaxies, particle physicists, and even just the basic physics of gravity and motion. And that progress and new and refined research questions are emerging from the need for concordance among these different specialties. Okay, so one more second here. I was thinking about that. I've been working on this with my students, trying to think of like, what are some possibilities for what could resolve this dilemma, right? Trying to basically compare all the different evidence from all the different directions and trying to see if we can get any insights into it. And as I was wrestling with that, it struck me that this process in practice is a lot like the process we describe much more generally of what we're doing in big history in relation to different disciplines, right? And bringing them together. There's sort of a container of big history for bringing different disciplines together to think about the shared story of our cosmic history. And so I tried to kind of capture that with this statement that I think, at least for me, one of the really important aspects of big history is that it provides this kind of container, like I said, for a universal framework within which many different ways of describing and experiencing reality can be considered and compared, right? And it highlights incompatibilities. Where does one model not fit with another, and where do they have overlapping themes? And then I also came across, at the same time I was thinking about that, came across an article in Inside Higher Ed about the state of academia and the lack of communication kind of among disciplines that we all talk about in big history community a lot. And so it got me thinking about this. So the word they use is dezoning, and in the sense of, neighborhood zones, right? And things are zoned for commercial, zoned for residential, and so on. And what I liked about their framing of it is that they emphasize this idea of compatibility as an organizing principle for the relationship among disciplines. And so I'm going to kind of adopt their language and just highlight a few things from their paper. The thing I like about it is that this idea of promoting an attitude toward knowledge that creates, so I highlighted in blue kind of the thread I want to take through this, a sustained effort in all disciplines to be adequate to each other, by which they mean creating knowledge that is consonant with the best explanations in other disciplines. And then to be compatible is to proactively engage each other's explanations, right? So again, just thinking about what we do in big history, and I think that's a good way to think about it, is that we're creating a container, like I said, where we can kind of do that. And then the exciting part is this last piece, right? If we open the gates that currently divide them, disciplines energized by a new compatibility could develop shared protocols for newly conceptualized research questions. And I was thinking about this a lot when I was listening to Kyle talk earlier this morning, right? About this idea of, this theme of information seen from all the disciplines of economics and physics and biology and big history and so on, right? And historians. Okay, so my suggestion is one way, again, just as we think about how to make the case to our colleagues who aren't familiar with big history, and we're trying to make the case about why this adds value when we're already super busy with our own disciplines and, in our own specialties, is this idea that it can be a much needed kind of prototype for the benefits of dezoning knowledge. And so last few minutes here, I'd just like to think about how we could shape that as part of the discussion. So again, I just repeated what I had up here before about how I see one of the core benefits of big history. And then the incompatibilities and common themes provide opportunities. I just listed a few here to expand and deepen our understanding, to articulate new questions, to develop new shared protocols for answering questions, again, in that overlap space. And then now I'm going to jump back for just a second to the dark matter problem for some inspiration about how to think about this. which is that this is what my current favorite idea for the answer to the dark matter puzzle is primordial black holes. They've kind of gotten a new life because of some recent data, recent analysis, I guess I would say. And so this is just a graph from a paper on the possibility that primordial black holes are the dark matter solution. But what I want to emphasize about it for now is just the structure, right? So this is just on the vertical axis is what fraction of the total necessary dark matter is met by the primordial black holes, where 10 to the 0 is 1. So it's got it filled. And then on this axis is what the mass of an individual primordial black hole would be in terms of solar masses, right? So this would be the mass of the sun here. And then the thing to look at is all these different colors, the lines, are different experiments from different areas. So this is limitations based on Hawking evaporation, because the black holes of certain sizes radiate at certain rates. This is from gravitational lensing studies. This is from gravitational waves. There's some other ones here. But just the idea that, right, so when we put all these in, this gives us a region where this could not be ruled out by any of them. So the reason I'm returning to that is I'm wondering if there's a way that we could think about this in big history, and just food for thought for all of you, is what would a parameter space, this is sort of like a quantitative Venn diagram, right, of what's allowed and not allowed. What would a parameter space like that look like to draw for big history, right? What would we include in there? Could we put, where does one field rule something out and where does some other field, overlap with that? Could we, just to be thinking about that. All right. And then some examples for things we could put on the diagram, in my mind, are the scientific story of, the 13.8 billion year timeline of cosmic history, right? That's solidly established. And the associated narrative, scientific narrative that maybe isn't so solidly established in some places. So we could think about that. There's our own just everyday subjective human experience of living in the universe, right? How we experience things and the stories we tell and the narratives we tell. The narratives of different cultures, more collectively. You could add lots of other things onto this, right? But just, part of my point in this talk is to encourage you to just think about that in those terms of how could you create a visual description of that? And I think big history could be a leader and a prototype for how to implement this kind of compatibility-based dezoning process, right? And how to energize disciplines through a new compatibility, as Bray et al. Suggest. And then the sort of add, I think, that this is not to say that we should make the disciplines go away by any means. It's the idea that we can complement the specialization of the disciplines and help overcome some of the blinders, right? So like there's a lot of value in being just a physicist or just a biologist or just a historian studying Roman history or something like that, right? And you develop a set of rules for what constitutes a valid question within your field and all those sorts of things that, while they help you dig down deep and get a lot of detailed answers, they also put blinders on you, right? And you get a limitation in terms of what questions you can even see anymore because you're so focused on that point of view. So I think putting a container that brings them together like this could really help. Okay, so my last point here is just something I think would be really valuable for IBHA to be a leader in this process, is maybe we could come up with a working document that would be kind of a compatibility protocol that we could, that we could invite people to think about, a list of questions about your field, if you're interested in seeing how it connects with other fields, that you could go through to help figure out collaborations and so on. So my thought is, if we put something like this on the website, the IBHA website, we could both give people some action items to kind of apply to their fields, and also make it a living document where people could contribute to it, right? And say, oh, I don't like this question, let's come up with another question, or so on. So anyway, so I put kind of a starting point for that, is, thinking about what one narrative emphasizes that we tend to ignore in another discipline, looking for similarities and asking where the problems are common. Again, I was thinking about this protocol a lot when I was listening to Kyle earlier this morning, right? About how could we encourage, he was saying that so few historians think about information theory in physics. How could we make that attractive to more people to do that in terms of thinking about this? Okay, so, and so I have it in the slides for people who want. Here are all the complete references on all these things if you want to follow up. And we're going to do